Hi. So far in this chapter, we've seen several concepts, right? We started with the concept of sequences, right? Infinite lists of numbers. And then we said, okay, what happens if we add all those numbers in that infinite list? We call these series. And we also looked at many tests that tell us when these infinite lists of numbers add up to a finite value and when they don't, when they blow up to infinity or do something else, something weird. We have started talking about power series as well, which is, well, it's also a series, right? But now it contains a power term in X. And again, we already saw that these power series can be viewed as functions of X, where we can also ask the question, what is the domain, right? And it turns out looking for this domain necessitates that we go back to tests for convergence, right? Specifically, the ratio test is one of the most useful tests you could do there. Now, what we're going to talk about in the rest of this section is, let's basically try to tie everything together and relate things back to, well, the functions that you know and love that you've seen so far in your calculus courses. Because as it turns out, we've developed all this machinery here, from sequences to series and testing them for convergence. What we're going to do at this point is look at functions and say, well, how can we represent these functions as these power series? For instance, is there a way to write sine of x as an infinite list of numbers added up? Is there a way to write ln of x as a series as well? And there are many, many nice applications to this, one of which is approximation. But we'll get to that later. For now, I guess suffice it to say, this is our roadmap so far in this section. And in this video in particular, we'll start talking about this fact, or this question, right? How can we represent functions as these power series for which we have all these things that we can use? So I'll give you an example to start. Take the function 1 over 1 plus 2x squared. Okay, so that's a rational function in x, right? 1 in the numerator, 1 plus 2x squared in the denominator. How do you even start representing this as a power series? Well, is there anything we can start with? Do you already know of a function that you can represent as a power series? In fact, I claim that you already know of one example. Remember your geometric series. The geometric series a plus ar squared, and so on, is a over 1 plus r, or a over 1 minus r, when the absolute value of r is less than 1. Okay. So why don't we write this with x instead of r? And let's just ignore the a for now. In fact, let's do 1 plus x squared, and so on to infinity. What is that? That's 1 over 1 minus x, when the absolute value of x is less than 1. Right, so I can express this as a sum, either as 1 times x to the n minus 1 from n equals 1 to infinity, or just to make this look a bit nicer, I'll have the index of summation start with 0, so the term can be written in terms of x to the nth power. Right, and so that's now a power series. And I'll write it up here because I will erase that line to give me more space. 1 plus x squared, and so on, or summation x to the n equals 0 to infinity. That is equal to 1 over 1 minus x for these values of x. just erase all of these. Right, and this is a power series representation of this function. Right, so we are allowed to go both ways. Instead of going from this infinite list and saying, well, this is the sum for these values of x, now we're going the other way. We can now say, well, I know what this looks like. This is the sum of this infinite list of numbers for these values of x. So let's apply that to this function over here. Okay, well, it's probably not clear yet how we can apply the same infinite sum. Well, look at what this is really saying on the right. This is saying this x over here, if the absolute value of x is less than 1, then it's equal to this infinite sum. And this function over here, 1 over 1 plus 2x squared, I can write that as 1 minus negative 2x squared. And doesn't that look exactly the same as this series on the upper right? Just with minus 2x squared replacing x. But now what this tells me is I can actually write this in the same way, just with minus 2x squared instead of x. Right, I'll write the next term just so we can see the pattern more clearly. Because this becomes minus 8x to the 6th power. And in fact, I can also write this using sigma notation. Again, just replacing x in that expression, minus 2x squared raised to n equals 0 to infinity. Right, and so this is a power series representation. You don't have all the powers of x, right? You only have the even powers. Right, that's fine. That's still a power series. Just so happens that some of your CNs are 0. Right, so if this is the general form for my power series centered at 0, then the coefficients here, well, they're equal to 0 if n is odd. And if n is even, what's the coefficient? Well, this is n equals 2. This is n equals 4. So we're actually dividing that power by 2 and raising negative 2 to that thing. Right, and now you can check. C sub 0 equals 1. C sub 1 equals 0 because it's odd. C sub 2 is equal to negative 2. That's correct. C sub 3 equals 0. And so on. So this is a power series. And in fact, we can also say where it converges. Where does it converge? Well, whatever this ratio was, right? Whatever this thing was inside the parenthesis must be less than 1 in absolute value. And you simplify this a bit, and you'll get minus 1 over root 2 to 1 over root 2. Okay, and I'll show you what that looks like. Oh wait, this should be plus. So this green curve here is the curve 1 over 1 plus 2x squared. And what I'm doing is I'm adding up partial sums of this series. So 0, 1, 2, 3, 4. Remember, the nth partial sum means stop at the nth term. So that's the first partial sum, just 1. For n equals 1, it's the same, because you don't have an x to the first power term. Well, for x squared, it's now minus 2x squared. Okay, that's 1 minus 2x squared. And look at what's happening. Like, if you zoom in really, really closely, you'll see that this red curve, which is my partial sum of the power series, looks like it's matching with the green curve, which is the original function. Right? Zooming really, really close. They're virtually indistinguishable. Right? And we know what happens when you keep adding terms of series. Right? You're getting closer and closer to the exact value if it's convergent. So n equals 3 doesn't change because you don't have a cubic term. When n equals 4, it's the function 1 minus 2x squared plus 4x to the 4th power. So it's even closer now, right? From n equals 2 to n equals 4, it's more accurate. And it turns out that if I keep adding terms, if I let n go to 6, that's what happens. And 8, and so on, and so forth. And so this is nice, right? This tells me that, okay, this power series representation, it looks correct. Insofar as, if I were to compute 1 over 1 plus 2x squared, right, the green function, it turns out that for these values of x, if I computed 1 minus 2x squared plus 4x to the 4th power minus 8x to the 6th power, right, I'm getting something really, really close to the exact value. And, well, maybe you're asking, like, why do we even need to do that if we're just computing the same thing? Well, look at this, right? It's a division, 1 divided by something. But here you're simply, what? It's a polynomial. It's just all multiplication and addition. It's just much easier to compute. So, what's nice about this? Well, imagine doing this for sine x or cosine x, right? Where instead of actually computing sine of x, you can just use this polynomial or a similar looking polynomial. But now the question remains, how am I able to get the series representation? Now, one technique that you can do is, well, as we did here, recognize the geometric series and apply it to your function. But other things you can do is you can actually take the derivative or even integrate these power series. Right? I mean, again, these are infinite polynomials. That's one way to think of it. So if that's f of x, that's my power series. What happens if I take the derivative? Well, the constant term disappears. This just becomes c1 times 1. This term becomes 2 times c2, so x minus a, power rule, right? The next term is 3 times c3, x minus a squared. And as a summation, I can write this as cn times n x minus a to the n minus 1, starting at 1, because the 0th term, the constant term, disappears. And the same goes for integration. You can integrate this, c0x. I can just add the minus a there. c0 times a is a constant. It's like a constant of integration. c1 over 2, x minus a squared. c2 over 3, x minus a cubed, and so on. And there will be some constant term here at the beginning as well. It's an arbitrary constant. And I'll give you an example of where this applies. Look at this series, for instance. I mean this function. X over 1 minus x squared. Like right now, it doesn't look like we can represent it as 1 over 1 minus a common ratio, right? Remember, this gives us the geometric series from n equals 0 to infinity, where whatever's in there goes in here. If I call this function f of x, well, I can write this as x squared over 1 minus x squared. Well, 1 minus x and then squared. Something you might do is to expand the bottom and write this as 1 minus 2x minus x squared and use this as your ratio. That's not going to look nice though. What that's going to give you is summation 2x minus x squared to the nth power. And sure, that is a power series in the sense that it's going to be composed of powers of x. But we don't have a general term for c sub n. Right? You just don't know what the series looks like. So it's not a good idea to do that. Instead, let's use the idea from the previous slide. What can you say about 1 over 1 minus x squared? Well, in fact, this is the derivative of 1 over 1 minus x. Right, just using the power rule. And so, as a power series, you can do this. Right, these two are the same thing, where it's convergent. And this is now sum n equals 1 to infinity and x to the n minus 1. Right? I'll do it step by step here. 1 over 1 minus x is 1 plus x squared, and so on. When you take the derivative, it's negative 1 over 1 minus x squared times negative 1 again because of the chain rule. And now I take the derivative of the right-hand side. It's 1 plus 2x plus 3x squared, and so on. Right? And this series. So, well, what now? We still need that x squared on top. So we just multiply by x squared. Makes the power go up by 2 for x. And now if you write it out, this will be just the same series that we saw on the right, with just an additional x squared factor. And, well, that's a power series now. And in fact, using sigma notation, we can just express this as n equals 2 to infinity. Just so we can write this as x to the n. I have n minus 1. Right? For n equals 2, the coefficient is 1. For n equals 3, the coefficient is 2, and so on. Right? We've adjusted the index of summation by 1, essentially. And that's a power series representation. And how about convergence? Well, we know this converges for these values of x. When you take the derivative, the previous slide said the radius of convergence stays the same. So it's still going to converge from minus 1 to 1. But then you have to look at your endpoints separately, just to check if the behavior at the endpoints changes. Here it doesn't. When you plug in negative 1 here, or 1, you're going to get a divergent series. So your interval of convergence here is minus 1 to 1. The radius of convergence is 1.